friends. Do you remember what we're doing?
Derivatives.
Yeah! Nice! Class dismissed.
All right.
All right, well done, Lou. So let's kind of do a quick summary of last time. Quick summary, because we're going to do something really, really amazing today. And I forgot to upload any of my Excel sheets, so probably, let me actually get this going. Because I'm probably going to want Excel out here in a minute. And you might too today, so if you have your laptop, and you can use Google Sheets too, it's totally okay. Oh, nice. Okay. I'm just going to open Excel because I know it's going to take a long time. I wonder if this is hooked up to that. I bet it is. Okay.
Truly is.
Yeah.
It's
I would have
everything.
actually dropped after that one if like he wasn't teaching the first
Yeah, that's the thing is that he is teaching us.
But I don't know if he's gonna do it next year.
The last two, this RC and the RCC and the one before, they're horrible. So bad.
I'm putting up, so this is the forward difference approximation of the first derivative. And let's put that, so this is a forward approx. And you can see why that's so, because we're looking at x and an x plus h. And we generally are assuming that h is positive here. I think it's mostly because there's a plus here, but we are basically, we have some point x, and here's x plus h. And so we're looking at those two forward, moving forward into a data set. This approximation is mostly used on the end of a data set when you don't have anything to the left. So this would generally be my first data value. And then as I moved into the set, I would switch over. Once I was in like here and I had neighboring points on the left and right, I would switch over to this formula, which is the central difference approximation. So that was x plus h minus x, f of x minus h, over 2h. And then what, do you remember what the order of error was on this?
Squared.
Yeah, it was h squared, yeah. And so this ended up being an incredibly, way better. So if this is within 0.1 of the truth, this is in with 1/100th of the truth. And remember that these are your error. This is how your error rolls. So here, I could almost think of my error as linear in terms of h, so just k times h. But down here, my error is going to be some constant, not necessarily the same one, times h squared. So again, if h is 1/100th up here, I've got error with, I've got like 1 decimal point of accuracy. And then down here, I'm going to have h squared is, so I'll probably have like 3 decimal places of accuracy in this case, just by simply doing it differently. There's actually no more information here. It's kind of interesting that this produces such a better approximation. So before we go on to the stuff today, I want to talk about how we could even just use these. Oh, let me put one more up here. This is if I'm at the end of my data set. So here's my data set. This is the last data point. And we'll call it x. Then in front of that would be x minus some difference, h. So if I'm at the right side of my data set, or the bottom, some edge of my data set, and everything else comes before that, then I would use this approximation, which is a lot like that one up there, except that it's f of x minus f of x minus h. Notice this is to the left of this, assuming h is positive, over h. And this is still not as great as that center one. So let me ask you to, like, I'm gonna really ask you to push your brains here. Just with the formulas on the board, how could we come up with, I didn't label this, this is a central difference approximation. How could we come up with a central difference approximation for the second derivative? Just using what's on the board. So let me pose that question and give you a second. How can we use, I'm going to call it star, to get a central difference, CD, approximation to F double prime? Take a second. How might you do this? You're in a pinch. Oh, there they all go. Got an idea, Lou?
Well, yeah, it just feels messy, but just,
Oh, it's going to be messy.
yeah, just using like our first derivative, so our first central difference, and then
Okay.
like substituting that in for the f's, but then you have to go back through and put in like f of x plus h, the derivative of that as like a whole thing into that.
Yeah, absolutely. Yeah. So is this making sense? How we'll do this? And this process is called bootstrapping. We're going to bootstrap this formula to whatever level we want. So here I would just say that f prime double prime of x is the derivative of f prime of x. So what I'm thinking here is that instead of having this f here, I'm going to replace that f with f prime. And I think this is what you were saying.
Yeah.
Yeah? And that's probably what Josephine was maybe thinking
What?
too.
I have no thoughts.
That's honestly, I envy that state. That's the state of perfection. Thoughts are just trouble. So I'm going to use the CD formula here. I'm just going to replace every f with an f prime. So this immediately becomes f prime at x plus h minus f prime at x minus h over 2h, and the error is going to be h squared. That's not changing. This has no, notice this has no reference to the function f at all. Doesn't matter. So this is somewhat, it knows about f, but it doesn't matter in the ways we're thinking about it. So then I'm going to go through, and I think this is what you're saying, Lou. Now I'm going to replace each of these with this. So let's think about how that might go. Go back to the original formula. And could you actually make the next move? It's going to be a little messy, but just use parentheses. And it's not that bad. Thank you. We're not out digging a ditch. Which actually sounds pretty satisfying. We're gonna dig math ditches. Get less blisters. Just be careful. Let me make one little, in case you're not quite sure. That argument there propagates like that. responsible. We're not responsible. That's my mantra. We've done nothing wrong. Thank you. Thank you, sir.
Of course.
Such an obtrusive table. Such a small room. Alright, so for this one, I'm going to replace every x with x plus h. So this is going to become f prime at x plus 2h. See, because I'll get an x plus h in here, and I'll be with that. What's this next piece become? And that shouldn't say, this should just say f, not f prime. What's this next argument here? F of x, yeah, because you got plus h, and then, plus h, and then minus h, and they cancel out, so you just get the sampling at x, and then the bottom's just 2h, that's all good. And this, remember, this is still all gonna be over 2h in the end. And then once we, does everybody see that? Because once you see that, you probably got the rest. I'm gonna wait till I get some verification, because I distracted Christian anyway during this. All right, I'll move on to this next one. You let me know. I'm going to trust you to let me know. So here now I'm going to replace every x with x minus h. So x minus h plus h, f of x, minus f of x minus h, x minus 2h, all over 2h. And then if we did a little work, got our fractions in order, that's going to be over 1 over 2h squared times something really pretty neat looking, f of x plus 2h minus 2f of x plus f of x minus 2h. Yes, sir.
What's your error?
Thank you. Good call. Keep that rolling along. It's going to stay h squared. Yeah, good call. Do we feel like we can do that? If we had to do it again or something? Now, we're not going to go for the third derivative, but we see how we could proceed. Ugh,
Yeah.
that's not going to be fun. That's like, sit down for 15 minutes and be super careful about it. But now we could use this to approximate a second derivative and have a pretty decent approximation. I just want to make sure everybody's on board with that, how I did that. Cool, could you find so then right now, could you find the forward second derivative formula? In the same way. Let's just do that, practice. See if we got it. So take this formula and come up with the f double prime of x for a forward difference. Let's just see what it looks like. I'm curious more than anything, and I want to just give you a little practice. Gotta be careful, don't you? When it gets really testing your understanding of functions. And then minus, f prime of x. So it's just the formula then. That's cool. That's lovely. I made way too much space there. Again, we get that h squared in the bottom. And then we're going to get f of x plus 2h minus 2f of x plus h plus h plus f of x. Does that seem reasonable? Cool, awesome. So now you really have mastered a lot of this. If you read through the challenge I gave you to look at in the book, I'm just gonna look at the wall and not make eye contact with anyone while I say that. But if you worked through that, you saw something pretty weird. Yeah? Cool. So I don't know if I want to go through it, because it's in the book. You can read it. You could watch me do the book steps, but you can also read them. What I want to talk about today is pushing these things forward so we can get all these central difference approximations. And remember where they came from. They all come from a Taylor series expansion. So if I have f of x plus h, I can write that as f of x plus f prime of x h plus f double prime of x h squared over 2 factorial, and then an f triple prime, h squared, etc. But after this, we have powers of h cubed or more in the Taylor series. So big O of h cubed. And is this notation, are we still good on this? Do we need any clarification on the big O? Because right now is the time to ask, because we're going to do something just insane with the big O. Just amazing. All right, I'm going to take your word for it. So you have in front of you basically what I'm about to do, but I'm going to kind of work this through. So this is just like notes for you. We're not going to read it together. I want to just show you what's on that page. And it's, like I keep saying, fairly incredible way to take a difference formula and boost the accuracy by 2 orders of magnitude with a simple move. And it's all because we understand this. These Taylor series are, I like to think of them as a mathematical prism. I feel like I've told this story to at least Cormac a long time ago. But certainly someone in this room has seen this. But I have this function f, and I want to understand its nature. So I pass it through the process of the Taylor series. And I like to think of that, like I said, as a mathematical prism. So think of that as a little bar of glass that I pass the function image through, and it breaks it into its fundamental frequencies. How much constant stuff is in there? How much linear stuff? How much quadratic stuff? Cubic stuff? Quartic? On down the way. And it tells me how much of each of those functions I need to build this function. So it's a really powerful and incredibly deep device. And thinking of it this way is just kind of beautiful, at least in my mind. I usually try to make things beautiful in my mind and I can memorize them better. Beauty sticks a little bit better than, and ugly also sticks a little bit better. So if we made a super ugly formula, we might remember how horrible it was, but we wouldn't remember the formula. So anyway, now I'm just starting to get weird. I'm gonna stop. Pulling myself back in, reeling him in, here he comes. So how do we boost the error here? Well, let's think about a pen that works. That's okay. Got a few rights out of that. So let's go back to that central difference formula really quick. We had f prime of x was f of x plus f of x plus h minus f of x minus h over 2h plus big O h squared. Hey, can you just really quickly on your paper, just to see if you're understanding this in multiple directions, can you draw a picture of a graph and prove to yourself that this is actually a derivative if I let h go to 0? What's the picture? What does the picture look like? Here's f of x, y equals that. Here is x, here's x minus h. I'll just remind you of it. I'm not going to make anybody suffer through telling me. But here's f at x plus h, here's f at x minus h. And this is the slope of that secant line, right? This is just 2h across. So instead of just using half of this to take the derivative, we use the whole thing. And what we can see is that this turns into the derivative faster than the normal derivative definition, which is usually just a forward difference. So somehow having information in front and behind is more than just at the point and ahead. So anyway, this picture, I just want you to see that this is also what's going on here. So anyway, this is a scheme, and I'm going to call it little g of h. It's a scheme for finding a quantity g. So this g is the quantity I want to estimate. This is my formula that depends only on step size to approximate this quantity. We're just assuming x is this thing and we're not involving x in g or in big G or little g. So this is my formula for approximating big G with step size little h. And then this is, of course, the error in that approximation. Just really saying a lot of the same things I've already said, just in a slightly different notational format, and kind of pulling back a little to make this apply to any scheme that estimates a quantity based upon a step size with a known error term. This can work for everything. And so we're going to see this later on when we go to integration. We're going to see this in other numeric schemes besides differentiation. And the thing that we're going to talk about is called Richardson Extrapolation. We are taking some things we know and projecting out of what we know. Remember, interpolation was things between things I know. Extrapolation is moving beyond the known into the unknown. And somehow this works so good. And the theory is actually pretty good. Sorry, I don't like this pen again. I guess it's time to buy a new box. We have to buy our own supplies these days. Okay. So let me write this in a slightly different way. So G, the thing I want to approximate, can be approximated with this scheme. And I'm going to just assume this error is essentially some constant 1 times h squared. The rest of this stuff will be negligible. So if h is small, h is like 0.01, this is 0.0001, and the h cubed would be even smaller. So relative to this, if h is small, this is negligible out here. So we're just going to kind of work from there. Let's say we do this approximation with step size h1. So put a little sub 1 in there. So we used step size h1 to get this approximation. And that this c is going to be different, but we're still going to get the same quantity. This will be true as long as we take our approximation and add on the appropriate error amount. We're going to do it again. Then, oh my God. Ah. Then, oh yeah, oh baby, that is a good marker. All right, look at that. Look at how lovely that is. Then with step size h2. and we're gonna assume that is not equal to the first step size. And so we're gonna plug that into our formula. Like maybe up here we took that formula and we used h as 0.5, and now we're gonna use h as 0.1 in this approximation and do it again. And this will have a different error because we have a different step size. So this error will either be bigger or smaller. We don't know. Depends on how these two compare. Yeah. So now we're gonna play a game. We want G. But what we're gonna do is try to cancel out this error here. We're gonna cancel out this error. And actually, let's put one more term. Can we put one more term here? I apologize. Can I put a D1 H1 to the fourth? Because our next one is going to be a fourth. We're only going to do this if we have these even terms in here, and you can see that this actually fits that bill. So D1H to the fourth plus order H1 to the sixth. There. And then the next term here would be D2 H2 to the fourth plus order H to the sixth. So these error terms are just series of even powers of H moving up. So I'm going to do some arithmetic. I'm going to multiply this quantity by a number and this quantity by a number so that when I subtract them, these cancel out. So look at the plan. I want to try to do arithmetic. Something times this plus something times this kills off this term right here. I want to just kill that off. So, and actually, sorry, this should also be C1. Apologies, C1, D1. Yep, cool. Because it's the same series. It's not a new series, so these coefficients are identical. So let's call this star. Let's call this pound sign. And I'm going to multiply star times H2 squared, and I'm going to multiply pound sign by H1 squared. And then these two terms will be identical. So we're going to now compute H2 squared times star minus H1 squared times pound sign, and see what that becomes. I'm going to do it to the left side and the right side. So on the left side, I'm going to have H2 squared G minus H1 squared G. Let me stop. Do you see how I'm doing this? Because I'm just kind of looking at the board rambling math, and that's never a good place to be for long. Just think of the main goal is to kill off those H squared terms. So everybody see how I got this left side? And if not, let me know, and I'll happily explain it. But it's really important that you do. So let me give you a second. And if you've already got that side, what's the right side going to become? And if you want to push it forward, do this and then solve for G. H2 squared G, H of 1, little g, minus H1 squared G of H2. These two cancel, and look at what happens. We're left with an H to the fourth term. Some constant in front of it, who cares? We got a new error level that's far deeper in than our original with a simple move. It's crazy. And now I'm going to take this and I'm going to solve for G, for a big G. So what will happen is that, factor, let me just write out my factor, and we're going to get G times H2 squared minus H1 squared equals, is H2G H1 squared minus H1 squared H2, and then we're going to have some error. Let's forget about the error in this. We've got some error floating out to the right. And now I'm going to divide both sides by H2 squared minus H1 squared, and I'm going to get G equals H2 squared, G of H1, minus H1 squared, G of H2, over H2 squared minus H1 squared. And this, my friends, is Richardson extrapolation. You make one estimate with a certain step size, another estimate with a different step size, combine them in this way, and you improve drastically your answer. It's insane. It's actually quite insane. So let's see, we could do a little just example here without me pulling up Excel. Let's just do that. So let's say here, let's take a known function, e to the x. I might need some calculator, friend, or so. I'm going to definitely need a calculator, friend. It doesn't always have to be Lou. Looks like it might be, though. That's okay. So let's say we want to approximate, and we'll call this f of x, so we can pretend like we don't know what it is. We're going to approximate f prime at 1. What should that be? What is the true answer here? E. Right? Because f prime of x is e to the x, evaluated at 1. And so we know that that's approximately 2.7, you know, all the good stuff that comes with e. So let's grab some points. First off, let's make this table so that a couple step sizes are available. So I'm going to do 0, 1/2, 1, 1.5, and 2. Check this out, because it's easier for me to explain this here when we go through. So I'm going to do a couple of these. A couple of these I got. That's 1. That I don't know. That is 2.7, 18, 28, 18, 28. That I don't know. I don't know any others. But Lou does.
I do. The half is 1.648721.
Thank you. That's great.
Okay.
And then the 1.5.
Yeah, 4.481689.
Thank you. And finally.
7.389056.
Did I get that right? 389056?
Yep.
Okay, cool. Thank you. So we got some nice data points here. Let's do an approximation with h equals 1. Now remember, I want to approximate f prime at 1, so I'm going to use a central difference formula. So first, use h equals 1. That's a pretty big step size, so we should not expect this to be great, but we'll see what happens. I haven't actually even done it with such a terrible step size. So the formula is like this: f at the point f prime of 1 is equal to f at your center 1, that's where you want to find your derivative, plus the h minus f at 1 minus the 1 over 2 times the step size. So that's my central difference formula. And I just remember that this is order h squared. I already knew that, but I'm just keeping it in my head. Yeah, this is an order h squared approximation. Here h squared is 1, so we should not expect this to be very good. Our error is going to be potentially quite large. But when I simplify here, I've got f of 2 minus f of 0 over 2. And we've got those cranked out. We wouldn't have done it if we didn't know those values. So this is going to be this number, 7.389056 minus e at 1. Yay, I can do that. So that's 6.389056 divided by 2. And I could do that, but I bet, oh my God. Did I do it? It seemed really natural. Does that check out on a calculator, or is there some kind of weird? Yeah.
Yeah.
Class dismissed. Again, third time today. Okay, cool. So that's terrible. Because we're looking, remember what we're looking for. The true value is going to be 2.71828, blah, blah, blah. That's the true value. We are off by a lot. Not sending any rockets to, I'm not going to say what I was going to say. I was going to talk about striking down a political figure, but I won't do that. Definitely not doing that. Okay, so now let's use h equals 0.5. Could you do that for me, please? You might need your own calculator. Lou can't help you. I pay Lou good money to help me keep my life.
Wait, I'm
order.
getting paid?
Oh, you haven't received a check. Let's start getting Excel up here. You already got it worked out, Lou.
Yeah, I was using Excel to give you all the numbers, so I just
Cool.
kept doing it
Freaking
there.
awesome. That's good. Good job, my friend. Good job. I'll do this with everybody because I think we're gonna have some Excel homework in here because man, it's good to use Excel. It's so awesome. At least the division will be easy. So it's, I don't think I can do this one in my head. I don't want to. I don't want to. What'd you get, Lou? What did Excel give you?
I got 1.0 for that.
For this
Oh.
the step size of 0.5.
Well, I just have the final, but for
Well,
the
that's cool. I just
subtraction.
want the final too.
Oh, the like.
Yeah, what just
Oh,
it should be the same.
divided by-
I think. Yeah,
When did you? Oh.
yeah.
Oh, I see. I was doing it wrong.
Okay,
It's
this is
2.
good.
It's 2.832968.
Yeah.
Thank you.
Oh.
Cool. Awesome. Cool. That's great. And you saw something. That's great. You
Yeah.
debugged your sheet too. So what a day. Probably not going to get a check this week though because of that. So all right. I know. What a chump. Such a chump. So Richardson extrapolation is going to improve these two by just a simple move. So remember how it goes. It is because, so this number in front, the power of h that we use here is the power of the error. So let me write the formula back up. So the extrapolated value is going to be h1 squared times our approximation using the second step size minus the second step size squared times our approximation using the first step size over the same, these things squared to the same difference. But what I want to point out here is that this power, if our order, I might have to show this on the board so that you can see this clearly. But if our error term had been order h to the 4th, as it is now after we do this, if it had originally been h to the fourth, I would have had to cancel that error term out by going to the fourth power. So this number up here, these squareds, are because our error was h squared. So make a little note here. Note, the power on the h's, and you can actually see this derived in that sheet that I gave you. I kind of did a slightly simpler version. I've got the general version in the handout. I handed out. On the h's, or the h terms, equals the order of error. And here that was 2. So now we go through and we crank this, and honestly, it doesn't matter who's h1 and h2. You can't go wrong, because if you do it different up here, it'll be in the same order down here, and everything comes out in the wash. So let's use h1 as 1. So here I'm going to say h1 equals 1, h2 equals a half. So I have to pick something. So this is going to be 1 squared times the approximation using the other step size, minus the other step size, which was 1/2 squared, times the approximation using the 1 step size, all over h1 squared minus h2 squared, and so that's 1 squared minus 0.5 squared. Now I for sure need a help on that. So let's see who can get there first. I'm going to start working on it right here in Excel. And if you get it, just shout it out.
I got it.
Okay, all right.
I got
Right,
two.
paycheck reinstated.
I got 2.712448.
What? 2.71? Just like this? Is that what you're saying, sir?
Yeah.
Yes. So we took 2 answers, neither of which look particularly good. And through Richardson Extrapolation, we improved them using an understanding of the series that lives underneath. That's where this all comes from. So Lou, let me record that here. What was that, sir? It was 2.71.
And I got 2448.
Awesome. Thank you. Incredible. It's literally accurate the first 3 decimal places if we don't round. I guess even if we do round, we've got 2.71 as our approximation from absolute garbage to start with. So this is a way to take bad data and turn it into good data in terms of computing the derivatives. So let me stop there, because that's kind of a powerful example, but I want to show you how we can keep building this up. And we're going to get a table that looks like a Newton divided differences table, and every time we increase the little triangle, we're going to get a squared amount of error improvement. Is this cool? Because I want to pull the screen down. Just let me know. Yeah? Christian, you're still right? Yeah. Okay, cool. Probably this is going to take good 15, 20 minutes anyway. So let's see what happens. And let's see if I can actually make this computer come through. So you might want to work along with me using your spreadsheet. Okay. Sorry, can you still see, Christian?
Yeah.
What you need to see?
Yeah.
Okay, cool. And I'll just start kind of working here with our friend. You done?
Yeah.
Okay. That's impressive. All right, let me wad up a shirt underneath this thing. Better. That's not bad. A little crooked.
Maybe you should put it on the card.
Lou.
God, I was just kidding. I was just kidding.
I don't think you were kidding.
No, I was, because
Okay.
I think that's
You gotta understand the power your words hold over me. I'll do it. You tell me to do it. Let's try to get, oh, there, yeah, that's okay. That's not bad.
So good.
Yeah, whatever. We're building fancy stuff in here. That looks like a fancy stuff builder. Right there. That looks like a rickety sack of shit is what it looks like. Alright. So let's make our first spreadsheet together. We haven't done this together, so this is gonna be fun. So, and I would like you to follow along. I would like everyone. Yes, my friend Thor, please. Here's- I hope that's not an offensive thing. Okay, good. It's like a cool thing, right? Like, somebody was freaking calling me Thor. Pretty stoked. So let's leave that first row clear. And then here we're gonna put our X, and we're just gonna label what we're doing. I'm just not sure what might happen above. And then here we're gonna put f of x. So this is like our sample. And let's create some samples. What do you think, what's a fun function we could try to approximate the derivative of? You guys tell me.
Natural log of x.
Good stuff. That's a great one. That was the one I was thinking too. That's a good freaking number. All right, so the domain is the positive reals, so we don't want to get too close, but let's do, oh man, we're gonna make this so good. So hold on, so here, actually change that x to step size. I'm sorry, I'm building this while we go along. Step size. Let's make this next column x and then the next one f of x. We'll see, we might even change that. So step size here is going to be 0, let's do 1, and then let's do a half, and then let's do 0.25, 0.1, 0.05. Why am I doing negative? I don't know. I don't mean it to be negative. It just came out that way. 0.1, and then here we'll do 0.05. So these are going to be our step sizes. And then let's move over to column E, and now put an x there. And this is going to be the point at which we take the derivative. So let's make that at 1 right off the bat. And let's think about what we're going to get too, because we understand this situation. We've got natural log, and we're interested in the derivative at 1 the way I've written it right now. And the derivative, if f is natural log, f prime is 1 over x. So we expect the derivative to be 1. So f prime at 1, the true value should be 1. That's what we're going to try to get at. All right, so then over here, this is going to say, let's make this x plus h. Let's make this x minus h. And I'm kind of doing this in a very slow way, but it's okay. And then this is going to be natural log, so you got to put equals. Oh wait, this is just words, isn't it? So this is going to be natural log of x plus h minus natural log of x minus h. We're just labeling our columns, and I'm kind of thinking it through, honestly, as we go through this. So let's get that all filled in. And I wanted to go through this together so I could show you, in case you haven't done a lot of Excel, how to do static variables and how to do variables in general. So for this B3 cell, I want that to add F1, whatever's in F1, to the value in A3. But I want to always refer to F1, and I'm going to do a cut and paste down the column. Maybe it's better to just do it. So here, I'm going to say $, F, can be capital or not, it doesn't matter, $1. And so now that will always refer to that number 1 up there, plus and we will do here A3. And that should have had an equals in front of it. So put in equals, sorry. You can go up to that formula bar and enter an equals. So now you see it's highlighting the two cells that I'm referring to, so I know it sees them, and it confirms that that's the stuff I'm adding. So that makes sense. We see that as a true result, and we feel like we got our formula. So now they have changed the filling in Excel. It looks like this is an old version, so you see that little square in the bottom right corner? We should be able to get that to a plus, drag that, and pull down, and it should propagate that pattern, and it does. This is great. I love old Excel. I hate the new version.
I don't think it's the new version. I think it's only on mobile apps. You have to click the fill button.
Is that what it is?
Yeah.
Boy, it's terrible. It's a big pain in the ass. Yeah, because I was working on my iPad last night. Oh, thank you. That's good to know. I'm super happy to hear that. And then,
function did you do at first? Sorry, I missed that. And it's like giving me weird things.
yeah, so everybody else, try to do column C, fill in column C. Just let me go right into
I think
No, it's cool. It's cool. Same thing here. You have no troubles?
I haven't even made this spreadsheet.
Oh, okay.
So,
So you need a $sign F dot. Otherwise, so let me show you, hit enter really quick so I can show you what happens. Now look at that formula.
Yeah,
See, it's moving that variable.
C?
So go back up to the
It's
first
that
one,
next
put
one is
$sign
H.
F, that locks the row, or the column. And then the second $sign in front of the number locks the row. And it creates a static variable.
just like that.
Yeah, and enter. Now pull that down. There you go. Good, yeah, exactly. You have trouble?
Yeah.
I just need to do it.
Oh, okay. Okay, okay.
I don't have any questions.
Okay, cool, cool. Anybody need help on this? Because I will ask you to do this at some point.
Question.
Yes.
Are we gonna get an error with the x plus h with the step size of 1? Because
Ooh,
we're doing control under
good.
0.
Yeah, because we will go to 0. That's a great call, Lou. Let's change that to 0.9.
Okay.
Safe side. That excellent point. We would have run into that in just a second, but you got us ahead. So here, this is basically kind of the same formula. $sign F, $sign. I mean, wherever yours is, you got to change it. It might not be F1. $sign 1 plus, and the thing I want to move is that reference in the column there. So I don't put $signs there. Keep it hot. And that doesn't.
Did you do minus or plus?
Yeah, I was like, what the hell did? Okay, I did plus. Yeah, thank you. I was like, how could they be the same? They can't be. Thank you. So let's do this. There we go. That looks way better. Cool. So we could in this next one go ahead and just do log of B minus log of C. But let's just go ahead and do the division as well in this step. So I'm going to actually rewrite this as, just so I have a note to myself, parenthesis around that difference divided by 2H. And that H is column A. We should have probably labeled it H, but hey, it's okay. So in here, go ahead and see if you can get that to work.
Is it just log times?
Yeah, log of. So yeah, that's a good question, Cormac. So we're going to do equals left paren, and then I think it is just ln. Yeah. And then left paren. Now you have to click in B. Click on B minus ln of the C cell. Close that paren, divided by parentheses, because I want to multiply the step size by 2. 2, you need an asterisk for times. Let's click back into A3. So I'm just going to leave that up for a second, because I see folks looking up there for reference. walk around. Does anybody need a helping hand? Happy to give that helping hand. If you're like really bold, we're going to do the Newton extrapolation in your next column. You might not be quite sure how to proceed with that, so maybe we should just do it together. But we're going to use neighboring step sizes as our H1 and H2. So in this first new cell, I'm going to do extrapolation with 0.9 and 0.5. And so it's going to have to flip which of these versions these are multiplied by. Think about that formula. But it's actually a pretty straightforward computation. So feel free to do that. Do it for these first two cells. Pick whoever you want to be H1 and H2. Put that over here. And then we're going to just go ahead and do the squared version, and then we'll tweak it. Because we're going to test and see if this is even working, and then we'll make it fancier. Can I hit enter here? Would that be okay? Everybody cool? So that is my approximate derivative. God awful, right? That is truly, truly terrible. But if you look at log, it's asymptotic right here. And so when we're at step size 0.9, our left endpoint is at 0.1. It's way over here. And it's just like very large magnitude. And so we expect that value to be pretty crappy because of that asymptote that we're approaching. So now just take that and pull it down. And it should give us all our derivatives. And look at, I mean, you can see as the step size improves how much better the approximation gets, right? That one with 0.05 is not bad. So let me stop. Everybody get there, please. You're good. Yes. Cool. All right, a little quick Excel trick. If you go up, see how this formula I wrote in D is spilling over into the E cell? If you just walk up and get the spot right between the columns and double click on it, it does an auto reformatting and makes it appropriate so that there's enough space for everything. So I just double clicked on that line between them. Let me do it again so in case you didn't see that. See, that's horrible. Better. Does anybody have a terrible precision set on their Excel sheet so you're only seeing like 2 decimal places of accuracy? Is that happening for anyone? Okay, cool. Because you might have to at some point set the formatting on numbers. If you need to do that, you can't figure it out, let me know. Let's insert a row above 2. So click on 2, the whole row. So we want to highlight the whole row, and then right click and click insert, and that should put a row above. There's a lot of ways to do that, but and the cool thing is it automatically adjusts all the formulas to be still consistent. So they're still all pointing at F1, nothing weird has happened. Just another reason to love Excel. Okay, is everybody with me? Because now we're going to extrapolate. All right, so this one here, we're going to put Richard Extrapolation 1. I'm just going to call it R1. And for now, anyway. And so what I'm going to do is I'm going to take equals. Remember how the rhythm goes in parentheses. I'm going to take H1 squared. So here I'm going to use 0.9. I'm going to click to the 0.9. That's my H1 squared times the approximation at the other H. So look at how there's that crossover. See how I'm squaring the value in the 4th row times the value in the 5th row. And I'm going to subtract. I'm going to do that in the other order. So now I'm going to take the second step size, click on A5, square times the D4, or whatever your approximation is, the one right above the one I just had. Close off right paren, over. Then you need another paren because now you want to do those H squared subtracted in the same order you see them in the numerator. You can literally just type it, it'll know. So you can type A4 squared minus A5 squared or whatever yours is. Let's make sure we're all getting that. terrible. But maybe better than that first one for sure. So let's stop and let's see that we're all getting to 0.85. Vivian, yes, did I screw something up, man? Oh yeah, yeah. You want to see the formula? Yeah. Let me. My gosh.
And
I-
if you double click on the cell.
Click or double
Yeah.
click. Oh, okay, gotcha. Thank you. Excellent. Is that what you needed?
Can you move a little more this way so I can?
I
see
can't.
this?
Oh yeah, yeah, yeah. Let's. How about we all know what's on the left side, so we're kind of
There
good.
we go.
Good old flannel. What can a flannel do? And let me know. Because now we can just pull that down. Once we get that to work, Vivian, are you still working on that? Or should I keep it up a few more?
Yeah.
Okay, so once you get that to work, right click in the lower corner, or excuse me, click on the lower right corner of that cell and pull down, but don't pull all the way down. Pull down to the second to the bottom row. Because it's referring to two rows, it's referring to the row below it as well, and there's no row below it in that bottom row. And what you should see is a series of Richardson extrapolations getting back. We're good? Cool. So I'm going to go here. I'm going to pull down. And oh my freaking God. And I'm going to pull it out. And if you extend that cell a little, you get to see way more precision. Look at that. Isn't that beautiful? It's really cool. It's just ridiculous. And this is all because of Taylor series. Literally, this is the understanding that fundamental structure underneath all functions, most functions, some functions. We improved this with no new information. Taking old information, we improved this in a way that's just a little astounding. What is the precision here? I mean, my goodness, we've got this out to like what, the 100,000th, millionth place, something like that. Okay, so let's improve this, because the goal now is to take these approximations and Richardson extrapolate them. So now let's in this row that says R1, let's change that a little bit, because we know we're doing Richardson extrapolation. So let's put big O of H squared there. That's the error. Well, that was all asked backwards because I had caps lock on. I wanted a big O. There we go. Little h squared. So that's our approximations there. Now in the next column, straight across, we're going to put big O of h to the fourth. You might want to take a save here. Done a lot of, and just don't lose this. I've done this lots of times, so I've got a bunch of sheets like this at home. But this will be your first very special Richardson extrapolation. So, how does this work? And what we're going to do is, I'm going to pull this up for a second. No. Cool. All right, so that is probably a fire hazard, so I better get rolling here. So the general Richardson extrapolation algorithm goes this, and it's in that sheet that I gave you. But in general, to improve an estimate with order h to the p error, it's probably going to be even for us. It doesn't have to be, but it's probably going to always be. To do this, get two estimates with different step sizes. And so we'll call that G of H1, G of H2. And this little g is a scheme, a formula with big O, H to the P error. You don't smell burning, do you? Okay, good. I'm just like super hyper worried about that. So to improve this, we're gonna knock out the order H to the P. So what this is saying is that our formula looks like this. True quantity is our scheme plus some constant times H to the P, and then plus some lesser stuff. We're gonna play the game where we multiply this by something, a different one by something, and cancel out that term, and then the next one becomes our error term. That's our new error term after that. So we're moving down the chain every time we extrapolate. So get these, and then compute H1 squared G of H2 minus H2 squared G of H, to the P, H1 over H1 to the P minus H2 to the P. Can you now, my friends, fill in the next 3 rows we need on that spreadsheet? You're gonna have to tweak the formula. And that does not smell good. I don't know, I smell like hair burning or something. It's,
Oh,
That's not good.
the back of your iPad case.
oh
The
shit.
keyboard part.
Oh my god,
The
okay.
keyboard part.
Let's not talk about this anymore. We won't.
Oh, it's fine. Oh, does not look fine.
Not good.
It's also a little foggy on the.
Yeah. Heard about that.
Oh fuck. It's like melted on there. Oh son of a bitch. Work on that, I'll be right back. See, who has cybered in here next? We don't talk.
Yes, sir. That seems like a bad plan too.
The very top's a little bit nicer. You can see the green
You see what?
bar. Like the green bar.
Yeah, that's good. That part's good. Yeah.
Maybe we use rubbing alcohol.
Oh, that's.
That whiteboard clears.
Yeah, that, or maybe one. These are completely dry. That's a good one, Cormac. Yeah, good thought. Good thought. Probably gonna crack the glass. That's the part I'm worried about. And I need to do it, I think, while it's kind of hot, right? It seems like. Oh. It's like really stuck on there. Oh my god. And this is how we end it.
You want like a card to scratch it off?
What's that?
Like a card to scratch it
Yeah, I think that's I think I'm gonna have to do it when it's. See, the problem is the glass looks kind of warped now, and I don't know. why that would be the case, but does anybody know if there's one in a different room? I think I might go look in just a minute. Now I can't see. Cool.
Crop that out of the video.
Yeah, this one's gonna send you a private link. This is gonna be not a public video. My goodness. Let me try one more thing here.
You just have a big jump cut and say, oh, I don't know what happened. It just paused itself.
Exactly. Exactly. Yeah.
Spooky Halloween.
One last try here. Let's try that. Does Cybert use this? He's probably gonna wonder what's happened.
Probably is.
And he might think he did it.
It's true.
He might not know what happened here. Okay, well. I'm sorry. I don't know. This is like I can't even see you because I've been looking in that light. My eyes are completely fried. Let's see. Can we even try? Maybe. Let's try. Oh my god. Maybe it looks better.
It's legible.
That's positive. All right. I'm just gonna do one. Oh, fuck. Okay. Good God. So one thing you could do is cut and paste this formula over to here and then just tweak it. Let me see. I think it has to be really big. Yeah, I think I'm going to be, and then I just change that to fourth. And that's honestly all I have to do. Change that power to the fourth power. And make sure that I'm referring to, yep, and I am referring to them, so that's great.
Do you wanna,
Did I not get them all?
or does it need to be H to the, so I think you have like the
Yeah, you had
X
the-
plus H.
I did the wrong thing to the fourth.
Yeah.
Oh yeah, you're right. Yep. Wait, did I? Oh yeah, I see. I changed the point to the fourth. Thank you. Oh my god. Where's my freaking step size? That's in A, right? Yeah. Okay. So this. Oh, we should have locked A. When I cut and paste over, it changed it to B. That's the problem. So that is A to the fourth. That should be A5 to the fourth, and then these are just A's. That's the problem there. Yeah, okay. God. And then just pull that down. And there we go. Yes, sir.
Is the next one you do H to the 6th?
Yeah, exactly. And so we would take this table out 2 more columns. The next one would be the 6th, and then the 8th would be our final one. And I'm just going to kind of run and just see if there's nobody in a certain classroom somewhere, and I'll be right back.
Which ones do you change to before? I changed everything before. I'm not sure if letting me the right answer.
Yeah, it should be everything to the front. I am assuming.
Alright, I got it wrong.
It was
Oh,
there.
I
Lou
think
was
you
Lou was
were
doing
wrong.
some stuff with
Oh,
this.
yeah.
No, so no. I laid this over.
And
And
almost
it
set it
melted
on
it.
fire.
Almost set it on
Yeah,
fire. We stopped that. And I've been trying to clean the lens.
Okay.
I knew he was Dr. Gray knows lots.
Yeah.
Yeah.
This should be.
That's
To the
oh, I
front.
see what happened
Uh-huh.
there. Yeah.
There's some goop on there and I cannot get it off.
Wait, hold on.
Okay.
I'm messing up.
Okay, let me
Yeah.
think about this. I think you probably need
I
some
think
kind
you
of glass
deleted the
polish on that.
Before you.
Okay.
That would
Okay,
be my
you can
guess.
Do you have
Uh,
something like that in
right here.
physics?
Have had some.
Okay.
Do we have some now? That's another question.
Okay. I guess I know what I'm ordering off Amazon.
I can look for it a little bit later.
Okay, thank you.
Yeah.
All right.
Sorry to interrupt.
No, God, thank you. It's like,
Looks like y'all are having fun in here.
we're having fun.
Last basically.
We're doing some weird stuff. Thank you, Fred.
Uh-huh.
Thank you. All right, friends. Yeah, could you please stop that like 23 minutes ago?